Hello guys, this is a video solution for the problem sheet for week 3. There are seven questions in this problem sheet. I will go through every one of them and give you a detailed solution. Please note that this video solution is on top of the typed solution and the handwritten solutions, both of which you can find on the course website. So the question 1 says that you have a random sample x1 to xn, IID, Bernoulli distributed with parameter p. All right, and the question is does the ETT, the extremal types theorem, hold? Now remember, Bernoulli is a discrete distribution, right? So what you need to do is to check the condition I gave you in the lectures holds or not. I can write down the condition you need to check is the following. I don't know whether you remember this. I will write it down again. So if the limit of this as k approaches w of f if it is not equal to 0, then this implies that ATT fails to hold, right? And this is a result I talked about in one of the videos, right? So this is what I'm going to use to answer this question, right? All right. First of all, you need to determine W of f. I don't know whether you guys remember the Bernoulli distribution. A random variable x has the Bernoulli. This is stuff you did in the first year, right? If the following is true, if the probability that x equals to k is equal to one of the following, is equal to 1 minus p if k equal to 0, and is equal to p if k is equal to 1. So the support for the Bernoulli distribution is either 0 or 1. All right. So what this implies that the upper end point must be, remember, the upper end point is the largest point of the support. So it's the larger point of 0 or 1, which is 1. All right. So what you need to find is the limit of, as k approaches 1 of this, right? So this is the limit as k approaches 1 of the probability that x equal to k divided by 1 minus f k minus 1. All right. So this is the same as the limit. You don't need the limit anymore because you just put k equal to 1. So you get probability x equal to 1 divided by 1 minus f at 1 minus 1, which is 0. Right? Okay, now the probability x equal to 1 from this statement we know is equal to p, right? And 1 minus f0 is simply the probability that 1 minus the probability that x is less than or equal to 0, right? Okay, the only value the x can take is either 0 or 1. So the probability that x is less than or equal to 0 is simply the probability that x is equal to 0, because there's no other value it can take apart from 0 or 1. So x less than or equal to 0 means x must be 0. And the probability x equal to 0 is 1 minus p. So this is p divided by 1 minus 1 minus b, which is equal to 1, which is not equal to 0, right? Hence, the ETT, the extremal types theorem, fails to hold. Okay. All right. So that's question 1, guys. Question 2. Is the following. So you have, once again, a random sample, IID, with the probability mass function, PMF, given by this. It takes the value 1 if k is equal to k0. K0 is a fixed number. And it takes the value 0 if k is not equal to k0. All right. The question is, once again, does the ETT hold? All right. So I'm going to use the same condition, right, as I did in question 1, right? So the first thing you need to figure out is the W of f, right? So here the support of the distribution is defined only at the point k equal to k0 and is 0 elsewhere, right? So the support is basically this point here where k is equal to k0. All right, so the upper end point must be equal to k0, therefore, right? So what we are looking for is the limit as k approaches k0 of okay, because k0 is a fixed number, okay, can do this, okay, and okay. Now we are told that the probability that x equal to k0 is 1. So the numerator is equal to 1 divided by 1 minus. This is the probability that x so now you should, once again, you should look at, just go about the probability that x is less than or equal to k0 minus 1 is it has to be 0 because I mean, as I said, the distribution is only defined at k equal to k0. So anything that is below or equal to k0 minus 1, there's no probability defined over this range. So this probability has to be equal to 0, right? So this will be 1 divided by minus 0, right? Which is not equal to 1, okay? Not equal to 0, I mean, not equal to 0. So hence, again, the conclusion is that okay, all right. So that's question 2 done. The next one is question 3. Question 3 is a little bit too hard for your level, so So I will ask you to ignore it, right? All right. I mean, I will not ask you anything like question 3 in the exam, so don't worry. Okay. Okay. So the next one is question 4. So question 4 is the following. You have right, the K. So the support of this distribution is from 1 to up to infinity, right? This function is known as the zeta function, is a popular special function, but you don't need to know anything about this to do this question. All right, the first thing you need to figure out is the support, the upper end point of the support. Here, the support being from all the numbers from 1 to up to infinity, the upper limit must be plus infinity, right? Okay, and so what we need to find is the limit as k goes to infinity of this. Okay, and this you can write like this. Okay. Right. Now 1 minus this is the probability that x must be greater than or equal to k. Right? Okay, so this equals to the limit okay. All right, so now what I'm going to do at this stage is I'm going to replace these two probabilities by the probability mass function that is given to us in the question. So replacing this, you get k power minus s divided by the zeta function at s. Replacing this, you get I okay. All right, so these two being constants, you can cancel them out, right? All right, so what you have is the limit okay. Right. Now at this stage I'm going to use a trick. you may know this or you may not know this. It's a trick in analysis. It says this, like if you have a sum from k to infinity of a function, say g is a function of I, then it can be approximated by the following. Right, as k approaches infinity. So this is I don't know whether you know this result or don't know, but under certain conditions. So I'm not going to state the conditions. This is true under certain conditions. Okay. I'm not going to tell you what they are, but for the purpose of this question, this can be used. That is, this summation can be replaced by an integral. As you know, integrals are easier to work with than summations, right? Okay. All right, so that's what I'm going to do in the next stage. So I will replace the sum by an integral. So the integral is going to go from k to infinity of x to the power minus s dx. Okay, so the integral of this is easy. You get take the limit from k to infinity. Okay, and if you take the limit at infinity, it will be 0. At k, it will be this. So assuming only it is 0 only if provided, or assuming that 1 minus s is less than 0. All right. So in other words, we need to assume that s is greater than 1 for the limit to be equal to 0 at infinity. So if this is not true, we can't do the question. Right. All right. So this is the limit as k approaches infinity of s minus 1 divided by k. All right. And this is clearly equal to 0. All right. So the conclusion is that hence the ETT does hold. Okay. Now, in order to check which of the three limits is attained, whether it's Campbell or Frasche or Weibull, you need to use one of the three conditions I gave you. So I'll leave that as an exercise, but I don't expect you to do this. Check conditions 1 to 3 to see which limit will be attained. All right. I will now do question 5 of sheet 2. Right. So it says this, that you have a random sample x1 to xn IID with the probability mass function and CDF given by the following. So the probability mass function is minus log right? And the CDF is given by right. The question is once again the support of the definition is k greater than or equal to 1, which means this. So the question is once again, does the ETT hold? All right. The first thing you must work out, or you must see, is the upper end point W of F. Now the support is this. So the largest point of the support is clearly plus infinity. So W of F must be equal to plus infinity. All right, the next thing to work out is the limit of this as k goes to the upper end point, which is infinity. So if this limit is 0, then the extremal types theorem will hold. If it is not equal to 0, it will fail to hold. Right? So that's what we need to work out the limit of this. That's what I'm going to do. All right, the probability x equal to k is given to us, which is minus right, and 1 minus the CDF at k minus 1 is 1 minus log base 2 okay. So the 2 1s cancel out. Okay, so what you have is the following. You have the limit of minus log 2. Now I'm going to write this as follows. Okay, and in the bottom you have log base 2 of okay. All right. Now the next step, now k plus 1 squared minus 1 is k squared plus 2k. Right. Right. Now as k goes to infinity, this goes to 1 and this also goes to 1. So you have log of 1 divided by log of 1, which is 0 divided by 0. Now what comes to your mind when you have 0 divided by 0 is the use of L'Hopital's rule. Right? So that's what I'm going to do. But before I use the L'Hopital's rule, let me rewrite this, right, as follows. You know that the log of a ratio is the difference of the logs, so you can right? Okay, now I'm going to use the L'Hopital's rule. Now, one thing I need to tell you before I can use the L'Hopital's rule is the following. Now, but when you differentiate the top and the bottom, what you need to do is basically you're differentiating log to the base, say a, of a number, say x, right? And the formula for this, the formula for differentiating this is as follows. I mean, in case you don't know this, you may want to note. This is the formula for differentiating log to the base of a of a number x with respect to x is 1 divided by log of a to the base e, which is the common log, times 1 divided by x. Okay, so I'm going to use this formula to differentiate this and this, right? So using the L'Hopital's rule, this is what you will get. Minus multiplied by log of 2, right, to the base e. But I'm not going to put e because log of 2 means is to the base e, right? Okay, and then you have plus log of 2, right? And in the denominator you have the following. You have 1 divided by log of 2 times k plus 1, and then you have 1 divided by log of 2 times k. All right, this is what you have. Now you see that all these will cancel out. All right. Okay, so this is what you get after using the L'Hopital's rule. Right, so let me rewrite this in a simpler form. You have in the top 2 times k plus 1 divided by k times k plus 2 plus, okay, and in the bottom you have 1 right. Okay. Okay. Now in the next step I'm going to this minus this, I'm sure all of you know. This minus this is minus of 1 divided by k times k plus 1, right? Okay, so dividing by this is the same as multiplying the top by this, all right? So you get the following. You get 2 k plus 1 squared divided by k plus 2, and then you get minus 2k. All right? This is what you get. All right? All right, now you can pull out the 2 is a common factor. So this becomes 2 outside. Now I'm going to use k plus 2 as a common factor in the denominator. So that means you get k plus 1 squared minus k times k plus 2. Okay. So this is the limit as k goes to infinity of 2 times k plus 1 squared. If you expand that, you get k squared plus 2k plus 1, and if you expand this, you get minus k squared minus 2k. Right, so you see that this cancels out with this cancels out with this, so you get the limit of 2 divided by k plus 2 as k approaches infinity, which is clearly 0. All right, so the limit of is equal to 0, which implies that the extreme of, so the conclusion is that the extremal types theorem holds, right? Now, to see which of the 3 limits is attained, whether it's Gumpel or Frechet or Weibull, you will need to check. You will need to check the conditions 1 to 3 I gave you earlier. But I don't expect you to do this. Okay, so this completes question 5 of sheet 2. Right. The next one is question 6. Question 6 is a bit too hard, and I don't expect you to know how to do it. I mean, if you can do it, that's great. But I will not ask you anything similar or close to being similar to question 6 in the exam or the test. So for the moment, for this course, you can ignore question number 6, right? So I will move on to the next one, which is the last question in the sheet number 2. Is question 7. So this is question 7. So you're given a random sample IID with CDF given by this. One minus q to the power x plus 1 to the power a, right? Okay, where q is a number between 0 and 1, a is a positive real number, and x can take values 0, 1, 2, etc. Right? So the first thing to figure out is w of f, which is the upper end point of the support, which is clearly equal to plus infinity. Okay? Alright, the next thing is to figure out the limit as k goes to infinity okay. Alright, now in this line I'm going to use, I don't know whether you know this property or not, but that if you have a discrete random variable, okay, suppose x is a discrete random variable with integer support. I mean positive integer okay, then the following is true. Then the following statement holds. I'm not sure whether you know this or don't know this, but if you don't know this, I mean, you should have learned this in year 1. Okay, this is a well-known result, right? So using this result, you can write the above as follows. Okay. All right. Now, I'm going to, in place of each of these, I'm going to substitute the given formula for the CDF. Okay, this is what you get. All right, you see the 1 and this one cancels, this one and this one cancel out. All right, so you get the following. You get the limit as k goes to infinity of okay. All right, now let's divide by the denominator. So you get the limit as k goes to infinity. This divided by this is 1. Okay. And this divided by this is q Okay, right. So the next page. Now I'm going to do the following with, you have this power k plus 1 power a minus k power a, right? So this you can write as I'm going to pull out the k term outside the brackets, so it's going to be this. Yeah. Okay. Now this you can write like this. These two are common factors, so you can write it like this. Right, in the next step, I'm going to use a result which is known as the binomial series. I don't know whether you know or not, so in case if you don't know this, I will write it down. You should have learned this in year 1, I think. The binomial series says the following. If you have something like 1 plus x power a, you can write it as the following. I from 0 to infinity of a choose I x power I, right? And this result is known as the binomial series, right? Okay, so using this, I can write this line here. Right, like this. Okay, all right. Now okay, let's see what the first few terms of the binomial series are. The first term, when I is equal to 0, you get a choose 0, which is 1, and this power 0, which is also 1. All right. When I is equal to 1, you get a choose 1, which is a, times 1 over k, so you get a divided by k. When I is equal to 2, you get a choose 2, which is a times a minus 1 divided by 2, right? When I equal to 2, you get k squared, and so on. Right? So these are the first 3 terms of the binomial series, and you're subtracting a minus 1, right? So you see these 2 ones cancel out, right? Okay. Now what you need to realize here is that as k goes to infinity, this term is much larger than this term, because here you have k power 2, here you only have k. So as k approaches infinity, this term will be a lot larger than this, and all the subsequent terms will be a lot smaller than this. So pretty much you can ignore all the terms after this, because this is going to be the dominant term as k approaches infinity, and you can ignore all the terms that follows this, right? So what I'm saying is is the following, that you can write this as the limit, 1 minus the limit of k approaches infinity of q multiplied by this only, because as I just explained, this term is a lot smaller than this, and all the subsequent terms are going to be a lot smaller. So the dominant term is only this one, which I have written here. All right, so this is going to be 1 all right. So what we need to do now is to find the limit of this as k approaches infinity. Now, we need to consider 3 cases. You will see why. All right, we need to consider the case where a is greater than 1, where a is equal to 1, where a is less than 1. Now, if a is greater than 1, then a minus 1 is a positive number, real number. So as k goes to infinity, this guy here will also go to infinity. So what you will get is the following limit. So let me put this curly bracket so you know what I'm doing. So you get 1 minus the q, 1 minus q to the power a times this guy here goes to infinity. So a multiplied by infinity, right? So a multiplied by infinity is infinity, but q is a number between 0 and 1, right? So that to the power infinity will be 0. So you get 1 minus 0, which is 1. Okay. All right. Now in the second case, when a is equal to 1, a minus 1 is 0, so k power 0 is 1. All right, so you get 1 minus q. This is the limit when a is equal to 1. Finally, if a is less than 1, a minus 1 is a negative number, so k to the power negative number as k goes to infinity is 0. So you get 1 minus q to the power 0, right, which is 1 minus 1, which is 0. So there are 3 possible limits, depending on whether a is greater than 1, equal to 1, or less than 1. When a is greater than 1, the limit is 1. When a is equal to 1, the limit is 1 minus q. And when a is less than 1, the limit is 0. So the conclusion to this question is as follows. Hence, the extremal types theorem fails if a is greater than 1 or equal to 1. The extremal types theorem holds if a is strictly less than 1. All right? So in this case, you can check the 3 conditions, conditions 1, 2, and 3, and see which of each of the conditions it is satisfied. All right? So if a is less than 1, check. All right. I don't expect you to do this, but if you have time, you can try to do it. Okay. So this completes question 7.